Before we can dive in and start talking about some real interesting physics, we have to cover some bases first. In order to communicate about any physical ideas, we need to have a unit, right? And we need to be able to agree on units. So units are, of course, super, super important. A number means nothing without units, and we will use the SI system, as you do in all your science classes, I'm sure. In this semester, we're primarily concerned with mechanics, which is the study of motion, energy, things like that. And so we're going to talk about the units used in mechanics first. In mechanics, we have three fundamental units. Those three fundamental units are the second for time, and for length, we use meters, and for mass, we use kilograms. So the second is probably the one of those that you're the most familiar with, right? 1 Mississippi, 2 Mississippi, that's a second. Maybe you've never thought, who decides how long a second is? You know, most of the time these days I look at my phone when I want to know what time it is. So is it Apple? Does Apple decide how long a second is? Other companies make watches. Timex makes watches. Does Timex decide how long a second is? No, they don't. It turns out the people that decide how long a second is, they live in Boulder. And they decide how long a second is by using an atomic clock. And so, you know, if we think about 1 Mississippi, 2 Mississippi, that's a very human construct, right? How long is a second? A second is definitely a human construct. And so the goal of scientists is to define these units. I mean, time is not a human construct, right? But seconds are a human construct. And so the goal of scientists is to define these things that we use, these units, in terms of physical quantities or ideas that are not human constructs, that are real parts of the physical world that we live in. And so that's what they've done with the second. The second is defined by a certain number of oscillations of a cesium atom. Why a cesium atom? I don't know. Because it's easier to make an atomic clock out of a cesium atom than it is out of some other atoms, for reasons we're not going to get into in this class. But basically, this atomic clock, it's called an atomic fountain clock. And what they do is this chamber right here is completely evacuated. It's a vacuum. There's nothing in there at all. It's like empty space. And they shoot a stream of cesium atoms up into here, which means they're in free fall. And so it's almost like there's no gravity. We'll talk more about that in chapter 3. So there's this fountain of cesium atoms goes up this tube here and then falls back down. And as it does that, they interact with this cesium atom by applying a magnetic field to it. And it turns out that when they apply a magnetic field to these cesium atoms, they oscillate in sort of an interesting way, in a very predictable way. And so these cesium atoms, we sit around and we wait for them to oscillate 9,192,631,770 times, and that's a second. So, again, a second is a human construct, but an oscillating cesium atom is not. In fact, if there was some civilization, some alien civilization, and we wanted to communicate about how we measure time, we could say, oh, well, I've been on the phone with my buddy for an hour, and they wouldn't have a clue what I was talking about. But we could describe how we set this atomic clock up and say, well, I was on the phone with my buddy for about, 14 trillion oscillations of a cesium atom, and we could communicate about that. Because a cesium atom oscillating in a magnetic field is not a human construct. It's just real stuff. Okay. So these folks in Boulder that decide how long a second is, at NIST, the NIST stands for the National Institutes of Science and Technology. And so the NIST F1 cesium clock is their current best and greatest clock. They claim it is accurate to 1 second in every 100 million years. And it turns out that that NIST broadcasts a radio signal that is timed very carefully with this atomic clock, and it broadcasts all over the country. Actually, it's on a frequency that your FM radio in your car cannot pick up. But anybody in industry or government or the military, anybody that needs accurate time can tune into this radio station and get what they need. So, there we go. That's the second. That's the first of our 3 fundamental units used in mechanics. The second fundamental unit used in mechanics is the meter, and that's how we measure length. And so the meter is about 3¼ feet. I don't know, it's something like that. So that's big or small depending on how close to your computer you are. Again, how do we define the meter? Well, it turns out not really that long ago. The meter was defined by the length of a specific metal rod. But what could be wrong with that? Well, let's see. What happens to things when they get warm? They expand. So, is a meter the length of this metal rod on a hot day, a cold day? Well, that means that your definition of a meter is tied into your definition of temperature. Ooh, we don't want that. We don't want that. And besides that, this specific length of rod that used to define the meter, it was stored in France. It turns out that that's a human construct again, right? We couldn't talk to some distant civilization and be like, oh yeah, it's we measure distance according to this rod that's over in Paris in a closet. No, that doesn't work, right? We want to base what a meter is, which is a human construct, on something that is not a human construct. And so it turns out that time, because of these amazing atomic clocks, time is the thing that we can measure the very best. And so we define a meter by combining our measurement of a second, which again is based on the oscillation of a cesium atom, and the speed of light. Cesium atoms oscillating, speed of light, not human constructs. So what we do is we say, okay, 1 meter is exactly the distance that light travels in a vacuum in this tiny, tiny fraction of a second. And since we can measure time so well, this turns out to be a pretty good way of measuring a meter. Again, we've tied it to something that is universal, that even a civilization in a far distant galaxy, we could agree on how to define a second now. Okay, how about mass? Now it turns out that mass is how much stuff. We're going to spend a little bit of time talking about that in chapter 4 and 5. What is mass exactly and how is it related to weight? It turns out, though, the quick story is that mass is how much stuff. In effect, it says how many neutrons, protons, and electrons are in an object. The units are a little bit goofy, but that's pretty much what mass says. How much stuff is in an object. And you know what? Until very recently, the kilogram was defined by the mass of a specific platinum iridium alloy cylinder that is kept at the International Bureau of Weights and Measures in France. This is a picture of a replica of that was commissioned in 1821. And so the United States has several of these around the country that are copies of this specific object. And up until recently, this was the definition of the kilogram. However, this is very unsatisfying for scientists because, again, this alloy cylinder, it is a human construction, right? We couldn't talk to some distant civilization and have them expect them to know anything about this particular cylinder, right? So this is just not really that great of a way to define a kilogram. And for many years, scientists have been searching for a better definition for the kilogram. And in fact, this is no longer valid. It was when I started teaching this class, but it is no longer the way that scientists define a kilogram. In fact, as of May 2019, the kilogram is now defined, again, by NIST, the National Institutes of Standards and Technology, by this device right here. And it is a complicated device, and it uses electric currents and voltages, which we can measure really well, to define the volt, and through a chain of algebra and logic, it all comes down to another fundamental idea that is not a human construct, and that is called Planck's constant. Now, what is Planck's constant? Ah, gosh. It's not quite so easy to wrap your brain around what that is, like the speed of light, or even oscillations of a cesium atom. That one's pretty tricky, but wrapping our brain around Planck's constant requires us to learn a whole lot of physics. So, for right now, I'm just going to say that Planck's constant is a fundamental constant of the universe, and we believe that a civilization in a distant galaxy would agree on what Planck's constant is. They would use different units to express it, but they would agree on that idea. And so, the point here is that now the kilogram has been redefined in terms of universal physical quantities and not in terms of human constructed objects. which is the goal of scientists. It turns out in May of 2019, there were a couple other units that were redefined. The Kelvin, which is the SI unit for temperature, we'll get to that a little bit later in the semester, that was redefined. And also the mole, which you might not think of something that needs a definition, but the mole, if you'll recall, is how many atoms you have to get together until you have the atomic mass number in grams of that atom, right? So that actually got redefined in 2019 also. Pretty interesting stuff. Okay, moving on. So, I'm not going to test you on the origins of these units, but I think it's interesting to know where they come from and why we use the units that we use. So again, in mechanics there are those three fundamental units: seconds, kilograms, meters. But there's all kinds of different things that we need to measure that cannot be measured in seconds, kilograms, and meters. For example, how fast. How fast is measured in meters per second. Meters per second, then, is a compound unit. It is a combination of the fundamental units. Other units we will use and encounter as we go through this semester. Power. If you look on your light bulb and it says it is a 100-watt light bulb, now you know that that is 100 kilogram meters squared per second cubed. Force is measured in newtons, kilogram meters per second squared. It turns out that the analogous English unit to force is the pound. So a lot of people think that kilograms and pounds are analogous. They're not. Newtons and pounds both measure force. Kilograms and slugs, a unit you've probably never used, those measure mass. So the English equivalent of a kilogram is actually a slug. Okay, so we need to know the prefixes, the metric prefixes. So there are some on either side of these. I will expect you to memorize these, however. And if you've had other science classes, then this is certainly not your first encounter with this. So if you see the prefix big G, that is giga, and that stands for 10 to the 9th. Kilo is one that we see a lot in kilograms, that is 10 to the 3rd. And so, basically the way this works then is if I have, say I have 14, megagrams of something, 14 megagrams, well then what I could do is I could look on this chart and I could say, 14 megagrams, well that is 10 to the 6th grams. And so this is exactly the same as 14 times 10 to the 6th grams. And so those are exactly the same. So that's how those metric prefixes work. Again, there are some above this and some below this. These are the ones that we use the most, and I think you should memorize these. It's really, really important to be able to do unit conversions effectively. So let's just practice doing this a little bit here. So this first one, convert 3 kilograms to slugs. Okay, in order to do this, you need to know how many slugs are in a kilogram. And it turns out that one slug is equal to 14.6 kilograms. Okay. So the way that I think we should be doing our unit conversions is like this. We're going to write the thing we're trying to convert. 3 kilograms. And then we're going to multiply this. And remember that you can multiply by 1 any old time you want, and you just get the same thing, right? I can multiply anything I want by 1. And we just get the same thing, right? Well, obviously this is 1, but you can write 1 in a lot of different ways, right? I mean, isn't that also 1? Right? So 3 kilograms times 1 equals the exact same thing, right? Anytime I multiply something by 1, I don't change it at all. That's a goofy way of writing 1, isn't it? But the point I'm trying to make here is that anything over itself is always 1. So anytime I make a fraction and the numerator and the denominator are exactly the same, then that fraction has a value of 1, and I can multiply it by something and not change it, right? So I could write this in a lot of different ways. I could write, 2 over 2. I could write, 2 times 2 over 4. Again, goofy ways of writing 1. I could write, I mean, we could even do a fraction of variables, right? 2x over 2x. Well, gosh, that's 1 also. A goofy way of writing 1. Well, guess what? Anything over itself is just 1. Well, if one slug is exactly the same as 14.6 kilograms, then can't I write this? And the value of that fraction is also just 1 because it's something over itself. That's what we want to do. So this is how I want to do our unit conversions, right? How do we decide whether the kilograms go on top or on the bottom? The answer is we want to cancel out the units that we're trying to get rid of. Here I'm trying to get rid of the kilograms, and the kilograms here are on the top. Therefore, my kilograms go on the bottom. Over there, I run my calculator, and I get 0.205 slugs. There we go. Okay. Groovy. Moving on. Let's look at the next one. Convert the speed of sound in air, 343 meters per second, into miles per hour. Okay. Well, this one's a little bit tricky because it's a compound unit that we are converting, right? And again, we need to know a unit conversion here. And let's say 1609 meters in 1 mile. Okay, so that is our conversion between meters and miles. We're going to use that here. Again, we write the thing we are trying to convert, 343 meters per second. And actually, I'm going to write this as a stacked fraction instead, because I think it makes it a little easier to see how we should write our conversion factor. Now, I have to convert both the meters and the seconds. I'll start by using the meters. Think to yourself, does the 1609 go on top, or does it go on the bottom? I think it should go on the bottom. And the reason is I want to cancel the meters here. They are on the top. Therefore, I need meters on the bottom over here in order to make that work. And here we see that now my meters cancel. And if I was to stop here and run my calculator, I would have a unit of miles per second. That's not what I was asked for. I was asked for miles per hour, so I also need to convert my seconds. And there are 3,600 seconds in an hour. Do my seconds go on top or on the bottom? If you said top, you are 100% correct. 3,600 seconds is the same as 1 hour. Now we run our calculator, and we get 767 miles per hour. So here's my answer. This last one's a tricky one. 3 meters squared into centimeters squared. Okay, so remember our conversion. 100 centimeters is 1 meter. 100 centimeters is 1 meter. Do my centimeters go on the top or on the bottom? Well, I want my centimeters on the top so that my meters are on the bottom to cancel. Now, many of you might stop right here. There are 100 centimeters in a meter, so we just multiply this by 100. 300 is your answer. That is not correct. Why? Because this is meters squared. If we're converting meters squared, we have to do this twice. If we were to just stop here, we'd have some goofy unit of centimeters times meters. I don't know what that means. So we want to do this twice. And we get not 300, but rather 30,000 centimeters. Okay. Unit conversions. important, if not the most exciting topic that we will talk about. But realize that the answer is wrong if the units are wrong, right? So it might seem like just a little detail, but really and truly it is important. And it can have real life consequences too. In 1999, this guy right here, this is the $125 million Mars Climate Orbiter. It crashed into the surface of Mars. Why? Because of a units mistake. The same kind of units mistake that my students make. NASA gave Lockheed Martin all of the specifications for this, what it needed to do, what they needed this thing to be able to perform. They gave the specifications in SI units. The contract indicated that they were using SI units, but the engineers at Lockheed Martin in Denver, they interpreted them as English units. And that was a $125 million mistake. Now this gal right here, in 2018, she was not careful about her units. And guess what? She missed a point on her homework. Yeah, real world consequences right there, people. Cautionary tales.